Hello there, now it is time to show you some more advanced features in HIL SCADA. These features are related to SCADA API and let you perform semi-automated testing. In this session, we will simulate two types of faults, phase loss and IGBT fault. Both of these faults will be executed for a predefined period of time. Also, let's capture these transients using SCADA API commands for executing the actions. These actions will be executed using Capture Handler. We will be continuing with our model from running your simulation module. First, let's open the panel initialization in HIL SCADA and define a global variable. This global variable will be callable by all the widgets in the SCADA panel. Let's define the variable global T fault, which will represent the period of the fault in seconds. Also, let's set the initial for duration of the fault to 0.1 seconds. Now let's insert a text box widget. With the text box widget, we can define an arbitrary period of time for our fault duration. Let's open the text box widget properties and rename it to fault duration, in seconds. Also, let's do a small modification in the macro code. Here we want to store the input value to the global T fault variable. We do that by calling the global T fault variable, and then by setting T fault to equal input value. Now let's add a macro widget. Let's open the macro widget properties. The macro is a special action widget that has 4 event handlers. The onStart handle is for code that will be executed at simulation start, just after the panel initialization script is executed. The onClick handle is for code that will be executed on a button click in a similar way to the button action widget. The onTimer handle is for code that will be executed periodically after simulation start based on the defined execution rate. The execution rate of this code can be 250, 500, or 1000 milliseconds. The onStop handle is for code that will be executed after the simulation is stopped. Checking the Active Handlers checkbox for a specific event handler will allow its macro code to be executed. We will use the onClick handler in this example. In the onClick dialog, let's write some simple code. First thing that we can do is to print the time duration in the message log. First, let's define the global variable T fault just like we did in the text box. Also, let's rename this macro to fault action. Now let's do a standard Python print command for T fault and click OK. Let's set the time duration to another value, 0.2 seconds for example, and confirm it with Enter. Now, we can run the macro by clicking on the macro button. In the message log we can see that we successfully printed the value from fault duration. In this way we managed to create an interaction between two widgets in the SCADA panel. This can be very helpful for semi-automated tests in HIL SCADA. Now that we can interact between widgets, we can go on to the next step. Now let's automate the operation of the contactor so that it opens when there is a fault. Let's go back to the fault action macro, and let's write some code. First thing that we need to do is to get the simulation time. Let's quickly go to the HIL API documentation and try to find it. To find the documentation we need to open the Documentation Hub in the Typhoon HIL Control Center main menu, and open the HIL API folder. Here we can do a quick search and write time. The first function, getSimTime is the one we are looking for. Let's call this function in the macro code and assign it to a new local variable simulation time. The comments provided in the code editor show the different ways to call various Typhoon HIL API libraries. Now that we have the simulation time, we can use it to set the state of the contactor at an explicit execution time. Let's use our API wizard to insert the HIL API function for setting the state of the contactor. Let's insert two lines of code. One will define the open state, and the second will define the closed state of the contactor. Next, let's take a look in the documentation for setContactor function. We can see that there is an interesting argument that we haven't used yet, the execute argument. This argument executes time commands on the HIL device with a time resolution equal to the simulation step. They are used when very precise timing is needed, for example when capturing transients as a contactor opens or closes. Let's add this argument and set the execution time based on the simulation time. Let's set the executed argument to be the simulation time plus half a seconds. This means that when we run this macro, the state of the contactor will change half a second later. For the close state, let's do the same thing, but let's also add the fault duration time. Now we can test it and see what we did. We should define the fault duration first. Let's put it to 1 second. Let's observe the machine speed. We can see that we have a drop in the speed of the machine, followed by a return to full speed after the fault duration completes. Now it is a perfect time to include the SCADA API for doing a force trigger from the fault action macro. Firstly, let's open SCADA API documentation and let's see how to execute actions using capture scope. All widgets in the panel have their own ID and fully qualified name or FQN. Let's find the getWidget by fully qualified name function in the documentation. The name of the function is getWidget by FQN. To get the FQN from capture scope, you need to right-click on the capture widget and click Copy Fully Qualified Name. Let's paste it as the value of a new FQN widget variable in the fault action macro. Let's use this FQN variable and add it as an argument in the getWidgetByFQN function, and assign this to a new variable called CS. Now it is time to see how to force the trigger in the capture. We will use the execute action function from the SCADA API. As we can see in the documentation, we have to add the widget handle and action name. For widget handle we will call the CS variable we made a few seconds ago, and for action we will use force trigger. Now let's save the code and open the capture scope window. When we click the fault action button, we should now see a capture appear showing the fault. Now let's include the IGBT fault as an option. Firstly, let's open documentation of the three-phase inverter. To open the documentation, let's click on the Help button. Here we can find important information on the functionality, control, and topology of the three-phase inverter. If we want to create an IGBT fault, we have to control one of the 6 IGBTs in the converter. In order to simulate fault of one of IGBTs in the converter, let's close the top IGBT switch in the converter. Let's add another global variable type fault that will tell us know which type of fault we want to simulate. Also, for this part of semi-automated test, let's use the combo box. Let's drag and drop it in the panel. Let's open the combo box widget properties. First, let's rename it to fault type. Here we have additional dialog. That dialog is available values. By the default we have case 1 and case 2. Let's rename these two cases as phase loss and IGBT fault. In the macro code we can see that we already have auto-generated if statement which we can use to define actions for each case. We can remove this. Now we can define our global variable to take the value of the input value from the combo box. As in the previous example, we need to define the global variable in the macro code so this combo box and the fault action macro can interact. Confirm the changes. Now let's go to fault action and do some small modifications. Let's create here a new if statement where we are going to ask what fault we want to perform. If the type fault is phase loss, then we will do the existing test. Else, we are dealing with an IGBT fault. In this case, we will need to set the power electronics switching mode and value. To do that, let's use help of API Wizard. Let's open the code editor. Let's open the switching blocks settings dialog and set software control to true for the SCADA top contactor. It is worth mentioning when software control is true, model control is overridden. This means that when there is an IGBT fault, the current in the S1 top contactor will be forced to 0. Let's do the insert. Then let's insert the code for returning software control to false in order to re-enable model control of the IGBT after the fault. Now let's add executed arguments to all 4 lines of code. We will again use half a seconds after the simulation time, and additionally adding T-fault for the last 2 lines. We can save it and close the code editor. Let's set the combo box to IGBT fault. We can see the waveform in the capture. Now let's set that the state of SCADA top is closed. In the fault action we need to set the value to 1. Let's perform the same test. We can see that we have a DTB flag raised. This is what we expected, since both contactors in phase A are closed, the software raised the flag. We can easily reset this flag by right-clicking on it. To summarize, in this session we showed you how to use HIL SCADA in a more advanced way. Also, we've found out more about using HIL API and SCADA API, as well as how to perform semi-automated tests in HIL SCADA.